In this video, we shall be finding the estimates of mean and beta for the Laplace distribution using maximum likelihood estimation. For more on this topic, you need to subscribe to this channel. The first thing to do is that we note that mu here is the location parameter. Also, beta is the scale parameter. We should also know that the sine function of x is equal to 0, 1, 0, minus 1. So we have x to be greater than 0, x to be equal to 0, and x to be less than 0. So this is the things we should note before we compute the maximum likelihood estimation for the Laplace distribution. So the first thing to do, if you want to compute the maximum likelihood estimation for the Laplace distribution, is to take the likelihood function. And the likelihood function of the Laplace distribution is equal to the product sum as I running from 1 to n of the given distribution. Mu all over beta. So this is what we get if we want to take the likelihood function. It then means that we can expand this because this sign means the product sum of the whole of that distribution. So we have it to be equal to, the likelihood function will be equal to 1 all over 2b, the first one, exponential, negative x1 minus mu all over beta multiplied by 1 all over 2b, the second, exponential, negative xi minus mu, the second one, all over beta multiplied by, it continues like that. You now get 1 all over 2 beta raised to the power of n exponential negative xi minus mu all over beta. This is what we'll get. It then means that our likelihood function of the Laplace distribution will be equal to, since it's the product sum, we'll now write it as 1 all over 2 beta raised to the power of n exponential negative, this is summation because we are summing n times of the values of xi minus mu all over beta. So this is what we get. This is what we get. The next thing is to take the law of the likelihood function. But we are not taking the law. We first rearrange this so that it will be very easy for we to take the law. So the next thing to do is to see the right this properly, which is the likelihood function of x to be equal to, this can be written as 2 beta raised to the power of minus n exponential summation of I running from 1 to n xi minus mu all over beta, which can also be written as 2 raised to the power of n minus n multiplied by beta raised to the power of minus n exponential negative summation of xi minus mu all over beta. So this is what we get as our likelihood function. The next thing to do is to take the log. Take the log. We'll take the log of the whole of this. So we'll move over to this other side to write it out properly. We move over to this side. So I'll be deleting the whole of this. So I'll be taking the log. Taking the log, we'll write it as the log of the likelihood function of the Laplace distribution will be equal to n. If we take the log of this, we get n negative n log 2. If you take the log of this, you have negative n log beta. If you also take the log of an exponential function, we get that same function, which is negative summation of xi minus mu all over beta. We take this as our equation star because we'll come back to it. So this is what we get. The next thing to do is to differentiate with respect to the mu. The mu, like we have already said, is our location parameter. So we say differentiate with respect to mu. To get the estimate of mu, we have to differentiate with respect to mu. So our partial derivative of the log of the likelihood function of the Laplace distribution is equal to, if we differentiate the whole of this, since there is no value for mu here, we get negative 0. If we differentiate the whole of this, the same thing, we get 0. There is no value, no parameter for mu. If we differentiate this, we get negative summation of xi minus mu all over beta to be what? Multiplied by negative 1. That means the value inside. So it then means that the log likelihood function of x mu beta is equal to this multiplied by this. You get summation of xi minus mu all over beta. So as I run from 1 to n, as I run from 1 to n, as I run from 1 to n. The next thing to do is to equate the whole of this to 0 to maximize mu. We equate the whole of this to 0. So we say equate to 0 to maximize this that is here. So maximizing it, we will move over to the next side as we are equating it to 0. So as we are equating this to 0, we have summation of xi minus mu all over beta is equal to 0, which also implies that summation of xi minus mu is equal to 0. So we have this. It then means that summation of xi minus mu is equal to 0. So this equation here, it is satisfied. This equation is satisfied when mu estimate is equal to the median of x1, x2 to xn. So this equation is satisfied when we know that this can be written as sine xi minus mu. So this equation is satisfied when mu estimate is equal to the